This is a continuation of Lecture 1. In the first part of Lecture 1, we introduced the concept of variable and data, and we talked about the different scales for data. We said we have categorical data and we have numerical data. And under categorical data, we introduced the nominal and the ordinal, whereas under numerical data, we introduced ratio and interval. The reason we did that is knowing the type of data is very important when it comes to summarizing data. So now we're going to talk about how do you summarize your data. So think about your survey, think about your research, your project. You've collected the information. Now you need to present this information in a way that is succinct and meaningful. The first step to do that is summarizing the data. So you have a certain variable, you need to summarize that variable. The way we summarize data depend on the types of data. So there are ways where we summarize categorical data, and there are ways that we summarize numerical data. We're going to start with categorical data because that's the easier one, and then we're going to move into categorical data. For categorical data, simply summarizing the data is based on two things. So here you have an example of categorical data, which is gender. So you have males, you have females, and then you have the numbers representing how many males and how many females. So this is called the frequency for a total of 50. And then you have a percentages. So 40 out of 50 is 80%, 10 out of 50 is 20% with a total. Okay, here's another example, educational status. Elementary, secondary, university graduate. You may notice that this is not only categorical data, but more specifically, it's an ordinal going from elementary to graduate. 5 out of the 50 have elementary education, 15 out of the 50 secondary education, 25 and 5. These numbers, these count, are called frequencies or count. Whereas when you turn them into percentages, obviously you get what we call a percentage. Okay? This is for categorical data. So basically for categorical data, what you need to do is you need to show the frequency or the count and the percentages. One question that you may be asked is, what is the point of showing the count? Whereas percentages are much more easier to interpret. The reason you want to see count is the fact that it will put things into perspective. Let me give you an example. One of the years, the school received a letter from the accreditation body saying that our passing rate of a certain exam, مثل colloquium, but in the US, has dropped from 100% to, I think it was, to 50%. And our failure rate all of a sudden went from 0% failure rate to 50% failure rate. Now we're looking at it as a percentage. It's scary. But the thing you need to realize is that the number of our students sitting for that exam, I think it was the NAPLEX exam, every year is no more than 2 students or 3 students, 4 students sometimes, 6 students. That specific year, we had 2 students that sat for exam, and one of them failed. Now, when one of 2 fails the exam, that translates into a percentage of 50%. Now, you look at it, it's a 50%, but in fact, it's just 1/2. In this specific example, looking at the frequency or at the count put things into perspective, and therefore we always need to have the frequencies or the count. In fact, there is a rule of thumb that says if your total sample is less than 30, you should not report percentages. You just report counts. All right, so let's continue with the slides. The second slide, مثل ما قلنا, summarizing categorical data. We use proportions or percentages. It's the same thing. Rates and ratios. ما حنفوت بالrates and ratios. We're going to stick to proportions and percentages. So basically, as I said, you need to report the frequencies and the percentages. And that's kind of like finish the categorical data. When we start talking about numerical data, then you have to address the concept of where the data is and how much variability there is in the data. Let me show you something. Well, let me clean this quickly. Let's suppose I'm showing you the grades of 3 statistic classes. So on class number 1 as the section 1, section 2, and section 3. Okay, so this is section 1, this is section 2, and this is section 3. And we're looking at the grades distribution. So let's suppose this is where the 70 is. Okay, this is the 70 and that's the 70. And the grades are distributed this way. So first section, this is how the grades are distributed. The second section, this is how the grades are distributed. And the last section is, this is how the grades are distributed. Okay. What I'm trying to show you here is that if you compare section 1 to section 2, you will notice that both of them are centered around, and if you look right in the middle, you see that both of them are centered around 70. Yani the average in both section is 70. Whereas if you compare to the last one, it's more around, let's say, 80. So obviously what's the difference between section 1 and 2 versus 3 is that section 1 and 2, both of them are centered around 70, whereas the third one is centered around 80. So section 3 stands out in terms of where the data is. However, if you compare section 1 to section 2, you will notice that in section 1, the grades are much concentrated in the middle, versus section 2, the grades are spread around. And therefore, the difference between section 1 and 2, though both of them are aggregated around 70, in section 1, students look much more alike. Yani there is much less variability in section 1 versus in section 2. And section 1 and section 2, section 3, when you look at how much variability there is, they're similar in terms of variability. This brief introduction introduces the two concepts of where the data is, where, okay, the answer to where the data is the central tendency, and where does the data tend to be. So that's the first concept of numerical data. The second concept of numerical data is how much variability there is, okay, and how much the values are different from one another, how much heterogeneous or homogeneous or heterogeneous the values are. And this is called the measure of spread. If everybody got 80 on the exam, there is no variability between the students, okay? If everybody got 75, there is no variability. But as students, some they get 70, some 75, some 80, some 82, 83, ببلش يصير في variability. And thus we would like to know how much variability there is. So when we talk about numerical data, we need to understand the two concepts: where the data is, يعني central tendency, and how much variability in the data there is, يعني measure of spread. Okay, so first of all, we're going to talk about central tendency, where the data is. For central tendency, we have 3 parameters that we calculate that will represent the central tendency: the mean, يعني الaverage that you know under the name average, the median, and the mode. We're going to introduce each one of them, and we're going to talk about the advantages and the disadvantage of each one of them. So what is the mean? What you're provided here is the formula. If you look at this formula, we have X bar written here. And that means this is the formula for the sample. But in fact, it's the exact same formula, even in the population. Yani if I were to write the formula for the mean in the population, I would write it, excuse me, I'm just going to clean it a little bit, the following way. I would say in the population, mu is equal, you sum up, هيدي معناتها you're summing up, you're adding up all the x's and you divide by the number of observation in the population. And the sample, as I showed you, x bar, is equal, again, you're summing up all the x's, but this time the x's in your sample only, and you're dividing by your observations in the sample. So I should put here capital N, and here I should put lower scale n. But these two formulas are equivalent, yani they're written the exact same way, except that here you're using population, all the population values, and here you're using only the sample values. Okay. The problem with the mean is that it's sensitive to extreme values or extreme observations. For example, if you're dealing with a sample and one of the values is too big, what that is going to do is it's going to pull the average up. Something that you may have encountered a concept of مثلا in exam بيقولوا فلان على الaverage. So everybody is getting like 70, 72, 75, and there's one student that got 100. That 100 will impact the average in such a way that it's going to pull it up compared to all other values. Okay, so it's sensitive to extreme values, which is true also for a very low value. If you have a very low value, also it will pull the average down. So here you have an example. In this example, we're looking at a sample of 18 individuals, and what we measured is something called variation in heart rate to deep breathing. It's a certain measurement that is used in health, and you have the values of these 18 individuals. The way we calculate the average is we're going to add up these values, so 19.2 plus 15.1 plus 0.9, all the way down to 46.3, and you divide by 18 because you have 18 observation. That will give you the mean 48.8. Since this is a sample mean, we write it as x bar. Okay. Now, if you look at this data, you will notice that we have two values that appear to be very big. اللي هن ال 86.1 وال 85.7. Okay, so هيدا ال 86.1 وال 85.7, these appear to be extreme big values, values that are very large. If we are to remove these two values and recalculate the average, and calculate the average without these two values, meaning that this time you're going to divide by 16, the new average comes out to be 44.1. The point being, these two values all by themselves have changed an average of 44.1 into an average of 48.8. Okay, only two values لحالهم علوا الافريج تقريبا 5 values. Okay, and that could be true if you have a set of data with a small values. So here's another example. In this example, we had, let's say, an exam, and 1, 2, 3, 4, 5, 6, 7 students. Their grades were 40, 74, 77, 78, 80, 82, and 88. Okay. Now, the student that scored 40 actually is a student that was sick on that day, and therefore he or she was allowed to take the exam again, and they changed their grade from 40 to 79. So what do you think the impact of changing a very low grade? Obviously 40 is a very low grade compared to the other grades. When you change it into 79, which is no longer a very low grade, what do you think it's going to happen to the average? So before we changed it, the average was 74. Okay, لاحظوا تقريبا كل الvalues are above 74, yet the average is 74. Why? Because of this small value pulling down the average down to 74. The minute that value is changed into 79, the average jumps to 79.7. Again, almost 6 values from only one value. Again, the point here that we're trying to make is that average, or mean, I should say mean, is affected by extreme values. Whether these extreme values are very large or very small, they do impact the mean. Therefore, a common thing people do, they calculate something called the trimmed mean. Trimmed mean معناتها a mean where you trim the maximum and the minimum. You get rid of the maximum and the minimum, just in case these two values are extreme or one of them is too extreme, and you look at it. The trimmed mean, in principle, is a mean free of extreme values. If your data does not contain extreme values, the mean should be very similar to the trimmed mean. They should be almost the same if the data does not contain extreme values. All right, so the first statistic we look at, or the first parameter we looked at, was the mean. The second one is the median. So what is the median? The median is the value that cuts the data in the middle if the data is sorted. Yani put the data from smallest to largest. The median is the value that comes right in the middle. Okay? And what we have here is not the formula to calculate the median, it's the formula to find the position of the median. And in the sample, we write it as x bar with this thingy right there. So the position of the median is the number of observation plus 1 divided by 2 will give you the position of the median, not the value of the median. Okay, so how do we find the median? Arrange the data smallest to largest or largest to smallest, it doesn't matter. And then find the n plus 1 divided by 2 position value. That would be your median. Okay, now if you have odd number of observations, the median will be a direct value part of your data. If you have even number of observation, you need to calculate the average of the two middle values. هلا حنعطي example and you will see that. Now, the median is less sensitive to extreme values than the mean, okay? And the median can be calculated for ordinal data. But probably what we want to stress on is the fact that the median is less sensitive to extreme values. Let's look at the example. We go back to the 18 values we discussed about the heart rate variation. The raw data looked like this. So when we calculate the median, the first thing you need to do is order the data smallest all the way up to largest. And then next, remember the formula says of the position, n, yani how many values you have. You have 18 values. You add 1, you get, so 18 plus 1 is 19. You divide by 219, you get 9.5. So 9.5 is the position of the median. ما في value that comes at 9.5. So you go down to the 9th observation and to the 10th observation. You get the average of these two values, and that will be your median. Okay, so your median is 43.6 plus 45.3. You add these two values, you divide by 2, you get 44.45. That is the median. Okay, now this data, if in case this value here was changed into 0, would that affect the median? The answer is no. لأنه the median does not depend on the actual values that are below it and the actual values above it. The median, the only thing about the median is that these values have to remain below it and these values have to remain above it. So if you take this value and you change it into a million, the median will not change. لأنه بعد this value on top of the median. ومن هيك we say that the median is not impacted by extreme values. In fact, if you remember, in the example when we were calculating the mean, we canceled the largest two values. Let's cancel again the largest two values and recalculate the median and see what happens. By canceling the largest two values, I no longer have 18 observation. I have now 16 observation, right? Okay, so what is the position of the median in 16 observation? 16 plus 1 is 17, divided by 2, you will get 8.5. So the 8th position is 42.6, the 9th position is 43.6. If you take the average of these two, it will be 43.1. So by deleting the largest two values, the median changed from 44.45 to 43.1. So it dropped by 1 0.4. Remember the average, how much it changed? It changed, if I remember correctly, by almost 5 units. So that again goes into saying that the median is less sensitive to extreme values compared to the mean. The same example we had regarding the grades 40 all the way to 88. تتذكروا كان الافريج 74. لما غيرنا ال 40 to 79 the average became 79 point something. Let's look at the median. What is the median in this set and what is the median in that set? How many observations do we have? 1, 2, 3, 4, 5, 6, 7. 7 plus 1 is 8 divided by 2 is the fourth observation. So the median is 1, 2, 3. The fourth observation is 78. Okay, so before the student was allowed to take the exam again, the median grade was 78. When the student was allowed to take the exam and his grade or her grade changed from 40 to 79, the median now becomes بعده, the fourth observation. So 1, 2, 3. The fourth observation is 79. So the median only changed from 78 to 79. Only a 1-point value change. Whereas if you remember when we were working with the mean, it was about 6-point change. Again, showing that the mean is much more sensitive than the median. The median doesn't change as much as the mean. One more example. In this example, what I'm doing is I have 6 values, 90, 94, 98, 102, 110, and 112. This data set, I add to it 2 values, 150 and 160. Obviously, 150 and 160 are large values, and I ask you, what do you think is going to happen to the mean, and what do you think is going to happen to the median? Okay? And I ask you to calculate the mean and the median for each example. Even without calculation, knowing that you added 2 large values, obviously the mean is going to get larger. In fact, the median is also going to get larger. However, based on the knowledge that now we know regarding the mean and the median, we expect the mean to be much more affected than the median. And therefore, we expect the mean to grow much more than the median. If you calculate the mean in the before group, so 90, 94, 98, 102, 110, and 112, if you add up these values and you divide by 6, you get an average or a mean of 101. So the mean here is 101. Now what is the median? You have 6 values, you add 1, you get 7, you divide by 2, you get 3.5, so the position is 3.5. This is the third, and this is the fourth. You add these two up, you divide by 2, the median is 100. Okay, so the mean can 101, the median is 100. By adding the 150 and the 160, now you're going to add up all these values, مع 100, مع 60, but this time you're going to divide by 8. The mean becomes 114. كان 101 صار 114. The mean grew by 13 points. What about the median? Well, now I have 8 observation plus 1 is 9 divided by 2 is 4.5. So the median position is 1, 2, 3, 4.5. It's the average of 102 and 110. So the median now is 106. It used to be 100. It became 106. So the median increased by 6 points, whereas the mean increased by 13 points. Again, this is to illustrate that the mean is much more affected by extreme values than the median. All right. What about the mode? I told you we summarize the central tendency using 3 things: the mean, the median, and the mode. قلنا شو المين، قلنا شو الميديان. The mode is basically the value that is most frequently observed. That is the mode. يعني if you're looking at a data like the one I drew when I was talking about the grades, okay? If you look at the data that looks like this, okay, right here on the top, okay, this is your mode. This is where the most frequently repeated data. It could be like this, and again, this is the mode of the data, okay? If a data is drawn and it only has one top, we talk about the data being unimodal. But if you draw the data and it has two or more tops, we talk of bimodal or multimodal data. معناتها the presence of more than one mode. Modes are not used a lot. We use much more the mean and the median. Okay, more about the mean and the median and the mode. When you have a symmetrically distributed data like here, what happened is that the mean and the median are very, very similar. Okay, for something like this, actually, let me just tell you what this is called. A distribution that has this shape is called the bell-shaped distribution, also called the normal distribution, also called the Gaussian distribution. Now we're going to call it the normal distribution, something like a bell shape. Okay, it's called a normal distribution. And in that case, where the top is, this is where you're going to have your mode, but also it will be where the mean is, and also it will be where the median is. Okay, so when you have something that looks like this, a normal distribution, the mode, the median, and the mean and the median are about the same place. Once you start adding extreme values on either side, so let's suppose that I'm adding extreme values here, very large extreme values. What's going to happen is that you're going to observe a shift. So Bado top is here, but then you have a shift like this. Okay, so let me draw it again so you understand how it's going to look like. Okay, so this is where you have extreme values that are large. It will look like this هيك وبعدين بتحسوا انه there's a tail on the side that has been pulled. This is called a positively skewed data or data skewed to the right. Okay, what happened is that your mode بعده هون, but the mean and the median were pulled up. Okay, the mean and the median are pulled up. Obviously, one of them has been pulled more than the other. Who is more sensitive to extreme value? The mean. So the mean has been pulled up more than the median. So that would be your mean, and that will be your median. Okay? So what does it mean? Well, it means that in this situation, the mean is actually bigger than the median. Okay? So whenever you have a positively skewed data, positively because this is the positive side, well skewed to the right, okay? Whenever you have positively skewed data or data skewed to the right, yani you have presence of extreme large values, the mean is going to be larger than the median. And the opposite is true. If you have a data with very small data points, كمان the distribution is going to be skewed, but it will look like this. Sorry, it's too pointy, but you get the point. Okay, so بعد المود here, the mean and the median have been pulled down because you have extreme values here. So one of them is going to be here and one of them is going to be here. The one that has been pulled further, يعني بعد أكتر, this is going to be your mean because the mean is more sensitive to extreme values. Whereas the one that was pulled less is the median. Okay? And what that means is that when you have negatively skewed data, or data skewed to the left, okay, the mean is smaller than the median. Okay, so here you have symmetrical distribution, the mean and the median are equal. Here you have positively skewed data, so you have large values here, pulling the mean much more than pulling the median, and therefore the mean is going to be larger than the median. And here you have a negatively skewed data, and you have very small values pulling the mean more than they're pulling the median, and therefore the mean is going to be smaller than the median. Okay, so again, here's a graph showing what I just say. In symmetrical data, the mean, the median, and the mode are right in one place. When the data becomes skewed, the mode does not change its place, it's still on the top. However, the mean and the median are pulled up. The mean is pulled more than the median, and the mean becomes larger than the median, and therefore we talk about a positively skewed data. Yani if you're told that in an exam the average is 70 but the median is 65, بما أنه the mean is larger than the median, this indicates that the data is skewed, positively skewed. يعني you have a number of students, few students that scored extremely high on the exam. If you're told that the average of an exam is 80 and the median is 79.8, the mean and the median are very similar, and therefore the data is symmetrical. If you're told that the average of an exam is 70 but the median is 77, here the mean is smaller than the median, and therefore there's a number of students that scored very low, pulling the mean down. Okay. Now here is just a point where I'm saying, in a sense, the median is the 50th percentile. Let me tell you what a percentile. A percentile is basically the value below which there is a certain percentage of the data. So when we say 50th percentile, yani 50% of the data is below this data point. And that's by definition what the median is. And the median below it في 50% or above it في 50%. So the median is the 50th percentile. If you're someone who's very, very smart, your RQ would be, let's say, at the 90th percentile. Yani below you في 90% of the people, above you في 10%. If the salary you're taking is a low salary, your salary might be at the, let's say, 20th percentile. شو معناتها your salary is at 20th percentile? Means that below you there's 20% of the salaries and above you 80% of the salary. So that's what a percentile is. Okay, so knowing that the median is the 50th percentile, yani 50 below it, then if the mean is larger than the median, in a positively skewed, the mean is larger than the median. This translates into the mean being above more than 50%. Okay, is more than the 50th percentile, and the mean أعلى من 50% of the data, and thus less than 50% of the data is above the mean. Okay, that's saying that 30% of the data was above the mean indicates the distribution was skewed to the right. If this is not clear, it's okay. It's just an illustration that might be a bit complicated. Here's a quick explanation again. So I was talking about distribution that is positively skewed. So it's skewed to the right. And we said in this situation, let's say this is the mean. And that is the median, for example. We said that the median is the 50th percentile. معناتها من هون ونزول في 50% of the data. And from here and up, there is 50% of the data. When you look at the mean is here. The mean is above all of this. Yani above the 50% and an additional percentage, which could be 10 or 20 or what have you. Okay? So when I say that the mean is below 65% of the data, above 65% of the data, that means the mean is below 35% of the data. That means that the mean is above the median, yani the data is positively skewed. Okay. So the question comes then, if I have three measurements to measure central tendency, or three parameters or statistics, which one do I use? Do I use the mean, or do I use the median, or do I use the mode? I already mentioned the mode is not used a lot, so let's focus on the mean and the median. If your data is symmetrical, then we use the mean. The mean has much more arithmetic characteristics than the median, and therefore we try to use the mean as much as possible. However, if your data is skewed, strongly skewed, and when I say skewed, it has to be really skewed a lot, and the difference between the mean and median has to be large, then we use the median. Also in the notes, we say that if you have ordinal data, we may use the median. For now, let's park this idea and let's focus on numerical data. So numerical data, if it's symmetrical, we use the mean. If it's skewed, use the median. And a way to know if the data is symmetrical or not, one thing you could do is look at the shape of the distribution, or you could look at the mean and the median and see how much they're similar or how much they're far away. If they're very similar, this is an indication that the mean and the median if the mean and the median are similar, this is an indication that the data is symmetrical. If they're far away, then this is an indication that the data is skewed. Then comes the other part that we need to do when dealing with numerical data is the measure of spread. And as I mentioned earlier, this measure of spread is a measurement of how much variability there is in the data, how much the values in a sample or in a population are different. And I told you that if in a class, let's say an exam, everybody got 75, then there's no measure of spread. There is no variability. The measure of spread is 0. By the way, if everybody gets 75 on the exam, the mean is 75, the mode is 75, the median is 75. Okay? So the three measures of central tendency are equal to 75. However, the spread is 0. There's no spread, there is no variability. Okay? So again, here we have a choice of measure of spread that we're going to cover, and there are the range, the interquartile range, the standard deviation, and the coefficient of variation. The range simply is just the maximum minus the minimum, and basically what this is doing is telling you over how many units the data is spread over. This is the range, maximum minus the minimum. So if you're looking at the grades on an exam, the highest is 90, the lowest is 60, then the range is 90 minus 60 is 30, 30 points. The way we interpret 30 points, we say that the grades of this exam are spread over 30 points. Okay, that's it. That's all you're getting. The range does not say much. It is just a spread of the data, the largest to the lowest. Obviously, the range is highly sensitive again to extreme values. So let's say all the values were between 60 and 80, okay, except for one value that was 95. That one value again is going to expand the range. So this is for the range. So one way to deal with the fact that the range is influenced by extreme values is to trim the range. So remember, I mentioned already the concept of trimming the mean. Trimming the mean, you're going to cut part of the higher and part of the lower. The range as well, you can trim it. How do you trim it? Well, I have to introduce the concept of quartiles. So what are the quartiles? The quartiles, as the name indicate, these are values that cuts the data into quarters. Quarters meaning four equal parts. So if you think about it, let's think about a data set, and I'm going to take a data set that looks like something like this. Let's say this is a data set, and by now we know that the median comes right here and cuts the data into 50% and 50%. Okay, so this is the median. also known, this is a revision, it's the 50th percentile, right? Okay. Then this data that has been cut by 50%, 50%, if you come and you cut that lower 50% in half, okay, so like the median of the lower part, then you get 25% here and 25% here. And if you repeat the same thing for the upper part, okay, if you cut it in half, like the median of the upper part, then you get a 25% here and a 25% here. And now looking at these 1, 2, 3 values, the data was cut into 4 equal quarters. The first quarter, 25%, the second quarter, 25%, the third quarter, 25%, and the last quarter, 25%. So whole 3 quartiles, we call them Q1, Q2, and Q3. So now you notice that the median, also known as 50th percentile, is also the second quartile, Q2. Okay? Type Q1 cuts the lower 25% of the data, and therefore we call it the 25th percentile. Okay? Q3, which cut 25 and 25 and 25, cuts the lower 75% of the data, it's called the 75th percentile. Okay? Alright, so to recap, any data can be cut into 4 equal parts, 4 quarters, using 3 cuts. These 3 cuts in Q1, Q2, and Q3, these are called the quartiles. Alright? Then the range used to look at the distance from the lowest value all the way to the largest value. That was the range. Now, if you look at the quartiles, if you look from the lowest quartile, yani Q1, up to the highest quartile, then that would be a range, but a range specific to the quartile, and therefore we call it the interquartile range. The interquartile range, or RQR, is basically the third quartile minus the first quartile. Mittelmer range is maximum minus minimum. The interquartile range is the largest quartile minus the smallest quartile. So the interquartile range is the distance between Q1 and Q3, and therefore it's covering 50% of the data, okay? But more specifically, the middle 50% of the data, okay? So the interquartile range, if we go back to the slides, okay, the interquartile range is the difference between Q1, Q3, and Q1. It contains the middle 50% of the data, okay, and it's the distance between Q3 and Q1, okay. So if the interquartile range is, let's say, for an exam, the interquartile range is 15, we say that the middle 50% of the grades are spread over 15 units. So here we're doing an example. I'm giving you the following values: 0, 2, 5, 8, 9, 12, 15, and 20. The good thing about this data is that it's already sorted lowest to highest. The first thing we're going to do is we're going to find the median. الميديان هو Q2. Okay? So the position of the median is the number of observation plus 1 divided by 2. So I had 1, 2, 3, 4, 5, 6, 7, 8 observations. Plus 1, that's 9 observations, divided by 2. That's 4.5 is the position of the median. So the median, you count 1 observation, 2, 3, 4, and 5th observation, you take the midpoint between these two, and therefore the median is 8.5. 8.5, the median, or Q2, split the data in lower 50% and an upper 50%. So that's the lower 50% and that's the upper 50%. Now to find Q1 and Q3, we have to find كمان the median of the lower section and the median of the upper section. You have 4 observation plus 1, that's 5, divided by 2, 2.5 observation. So Q1 is the average of the second and the third observation. Therefore, Q1 is 3.5. Same thing for the second part. So this is the second and this is the third observation. You take the average of these two, and that would be your Q3. So Q1 is 3.5, Q3 is 13.5. The interquartile range is the Q3 minus Q1 equals to 10, and therefore the interquartile range is 10 points. Remember, the range of this data is maximum minus minimum, yani 20 minus 0. The range is 20, yani this data is spread over 20 points. The interquartile range is 10, meaning that the middle 50% of the data is spread over 10 points. The problem with the IQR, it's discard too much data. Hence, what should we do? What we're going to propose is something that maybe intuitively you might think about it. So intuitively you say, okay, well, if I have multiple observations and these observations are spread, so I have maybe an observation here, an observation here, an observation here, an observation there, an observation here, an observation here. If I want to see how much variability there is, how about I look at how much far away these values from one another and get the average of these distances, okay? So intuitively, this makes sense. You may say, okay, let's see how much far away these values are from one. So let me calculate the distance from here to here, here to here, here to here, here to here. And also let me calculate the distance here to here, here to here, here to here, and here to here. And then I do the calculation of from here to here, here to here, and here to and so on and so forth. And I calculate all these distances and I get an average of these distances. Well, intuitively, this makes sense. In fact, it doesn't work. And the reason it doesn't work is that you're doing a lot of overlapping between these values. So a better way to do it is, instead of looking at the distances between every and other observation, the better thing to do is to find a reference point for all these values and see how far away these reference points are from that value. What could be a good reference point? Obviously, the best reference point is the mean. Okay? So what we do is we see how far away is every value from the mean. You calculate these distances or these differences or these deviations. So you calculate the deviation of every value from the mean. Okay? Then you sum up these deviations and you get their average. هيك بيكون we've calculated an average distance of the values from the mean, or what is called a standard deviation. However, the problem is if you calculate the deviation, so the formula so far is that you're going to see how much far away every value is from the mean. Okay? So if you take the mean minus the value, so you're doing that for every one of them. So this is x bar 1, x1, this is x2, this is x3, this is x4, x5, and x6. So if you do mu minus x1 and then you do mu minus x2, x3, and then you come to add these together, okay? You want to add them up and you want to divide by n, okay? The problem is when you add up these values, some of the distances is going to be a negative value. So if I'm doing mu minus x whole are going to be negative, whereas these are going to be positive distances or differences. And by definition, the mean is the point that average out these distances. And therefore, if you were to come and sum up these distances, automatically you're going to get a zero. You get a zero. Okay? So though the rationale, the way you're thinking about it is correct, let me see how far away is every value from the mean, and then I calculate the distance of every value from the mean, and then I add them up and divide by the number of observation. The concept is correct, but the problem is some of the differences is positive, some are negative. You add them up, automatically you get a zero. So that doesn't work. So how do you solve the problem for the zero? Here, two suggestions usually emerge. One suggestion is to take the absolute value of the differences. That might be a solution, but it's not the better solution. The better solution actually is to take the square of that distance. So you take mu minus x, you square that, okay? By squaring, you got rid of the difference of the negative and the positive, so they're now all positive. You add up these squared differences, which, by the way, this is called the sum of squares. So if you ever see me write SS, meaning sum of squares, that's what this is. It's a sum of squares. So you sum the squares and then you divide by the number of observation. Now, obviously here you have a problem, which is the unit is a squared unit. So to go back to the original unit, you need to square root all of this, and that is what is called a standard deviation. Yani an average distance, standard deviation, deviation from where? From the mean. A standard deviation, yani an average deviation. And so this is called a standard deviation. Okay? Now, let me write it again so that it's clear. So we said that what we can do is we can calculate the deviations from the mean, and then we're going to add them up. To correct for the problem that some are negative, some are positive, we're going to square every deviation, and then we're going to sum them up. And then you're going to divide by the number of observation. This is called variance in statistics. Okay? So if you stop here, this is called variance. The problem of the variance, it is a squared unit. So for example, if you're calculating the standard deviation of weight, the unit of the variance is going to be kilogram square, which is not easy to interpret. So to solve the problem, you're going to take the square root of this, and you're going to square root the variance, and that is going to give you the standard deviation. Okay, this is the standard deviation, and since we're working in a population, this is going to be called sigma. Okay, so the formula of the sigma is the population average minus every observation. You square that difference, you sum them up, you divide by the number of observation, and then you square root. That will give you the standard deviation in the population. Now, there is a problem when you're working in a sample. When you're working in a sample, you do not have the population mean. If you do not have the population mean, then you need to replace it with the best thing you have. And the best thing that replaces the population mean is the sample statistic. Okay? So you're going to take the x bar instead of mu. You're going to do the exact same thing we've been talking about. Okay? You're going to square and you're going to sum. However, when you come to divide, you're not going to divide by n, you're going to divide by n minus 1. I'm going to explain that in a minute. Okay? And then you square root, and that is your standard deviation in a sample. Okay? So the difference between the standard deviation in the sample and the standard deviation in the population. In the population, you're using mu, and you're dividing by n. In a sample, you're using x bar, and you divide it by n minus 1. All right, so why do we divide by n minus 1? Why don't we divide by n? It's a complicated thing, but I'm going to try to explain it the best way I can. All right, so remember early on in this course when I was explaining the difference between population and sample, in a population, you have parameters, whereas in a sample, you have statistics, right? All right. And remember, the role of the statistics, their role is to do what? The role of the statistics is to estimate the population parameter. Okay? That's what they're doing. Okay? So you have a population parameters that we don't know the value, and the sample statistics are the role is to estimate. Okay? So the first parameter that we covered can el mean, for example, which we said that the mean in a population is mu, and we wrote it as sum of all the x's in the population divided by the population size. In the sample, the estimate of that mu is x bar, which is also summing up all the x's in the sample divided by the sample size, which is n. When we come to the standard deviation, which is sigma, okay, in the population, the value is sigma, which we do not know. In the sample, it's s. And the role of s is to estimate sigma, right? So this is trying to estimate that. However, when you're trying to estimate the sigma, in the formula that we just covered, we said that you're going to do x bar minus x, you square that difference, you add them up, and then you come to divide. Now the problem that should pop up to your eyes is that while you're estimating sigma, inside the formula, you're not using the real value, you're actually using an estimated value. Therefore, while estimating, you are using an estimate. What that does is that you lose what you say a degree of freedom. And therefore, you do not divide by n, you divide by n minus 1 because you lost a 1 degree of freedom. Okay? Remember, to be able to calculate this x bar, you had to do this. Yani you already had to use the data once. Since you already used the data once, when you come to estimate s, you no longer divide by n, you divide by n minus 1 because you are using an estimate part of your estimation. Okay? In fact, there are other parameters like the skewness and the kurtosis. These formula, when you want to calculate the formula, in the population, the formula requires mu and sigma, part of the formula, to calculate the population length. I think it was kurtosis maybe. Okay? So when you come to estimate it in the sample, you do not have mu, so you're going to replace by x bar. You do not have sigma, so you're going to replace by s. And therefore, when you come to divide, you're going to divide by n minus 2. Why you're going to divide by 2? Because while you're estimating, you already used 1 and 2 estimate. And therefore, you divide by, and we say the degrees of freedom is n minus 2. For the fourth parameter, you're going to need mu, you're going to need sigma, and you're going to need the third one, which I think it was kurtosis. And therefore, while estimating the fourth parameter, you're going to use your first estimate, your second estimate, and your third estimate, and therefore you're going to divide by n minus 3. Okay? So the point being is the following. Every time while you want to estimate a parameter, you're going to use an estimate part of your estimation, you lose a degrees of freedom. You lose 1. And therefore, you do not divide by n, you divide by n minus 1 for the standard deviation. And therefore, the formula becomes the following. قلنا in the population عادي it's sigma of mu minus x square divided by n population over square root. هون لأنه we're not doing any estimate. Whereas when you're doing a sample, which is the case that we're going to do in our class, we'll never calculate the population. We'll always calculate the estimate. So part of your estimate, you're going to do the summation, and you do not have mu, so you're going to replace it by x bar, which is an estimate, minus the x. You square these differences, and instead of dividing by n, you're going to divide by n minus 1 because you lost what we call a degrees of freedom, and therefore the formula becomes like that. I can rewrite it as, remember I said this is sum of squares, so I can write sum of squares divided, this is, I call that degrees of freedom, okay? So sum of squares divided by degrees of freedom, and you square root, that will give you your standard deviation, okay? So going back to our notes, this is an explanation of what I explained, that intuitively you want to look at the differences between the observation. You need a reference point. The best reference point is your mean, okay? So you're looking at the distances of every value to the mean, okay? And you think, okay, let me add them up, divide by n. The first problem you're going to encounter is that adding them up is going to give you 0. And here's an illustration. So here you have 1, 2, 3, 4, 5, 6, 7, 8 observation. The mean, يعني الx bar of these observation is 81.5. If you calculate the distance of every value to the mean, يعني x minus mean, you're going to get these values. If you add them up, you get 0 automatically. That's the nature of the mean. The mean, you can think about it, it's as if it is the central, it is the, in physics it has the name where equilibrium stands. So it's right there where all the differences add up to each other to get a 0. Okay? Therefore, we cannot use just x minus mean. We have to square the differences. هلا أنا when I was explaining حطيت ال x bar بعدين حطيت ال x. It doesn't matter. We are squaring. Okay? So you're squaring the differences, then you're adding them up. That's the sum of squares. Okay? And then sum of squares divided by the degrees of freedom gets you the variance. Then you need to take the square root of the variance to get you the standard deviation. Okay, so the standard deviation, as the name indicates, it is the average deviation of the value from the mean. On average, how far away every value is from the mean. Okay, and we pointed out that you're dividing by n minus 1 when you're working in the sample, and you know that because you have x bar. Whereas if you were working in the population, you would not have to divide by n minus 1. In fact, if you have scientific calculators, you will notice that in your calculators, you're going to see 2 standard deviation. You're going to see one that looks like this with an n next to it, and you're going to see one that looks like this with n minus 1. In the calculator, what they mean, this is meant to be the population sigma that we call this population sigma, and this is meant to be the sample standard deviation, which we call S. So نحن this, we do not call it sigma and mine, we call it S. يعني this is an estimate based on the sample. It's not the real population value. That is the real population value. This we calculate it all the time to estimate this one, which most likely we will never know. Okay? So here's again the example that I showed you, the values, the mean. This time I'm squaring the differences. You add them up, you get 877.5. So this is the sum of squares. You have 8 value minus 1, that's your degrees of freedom. Why we're doing -1? Because we're working in a sample. So while estimating, we used an estimate, which is this x bar. This x bar is my estimate. You take the sum of squares, you divide it by the degrees of freedom right here. This is your variance. You square root the variance, you get the standard deviation in the sample. Okay? Now, um, what can we learn about the standard deviation? Well, there is a rule of thumb about standard deviation that says if you take the average and you go 2 standard deviation up and 2 standard deviation down, you will capture at least 75% of the observation. This is at least, okay? يعني regardless of the distribution, no matter how the shape of the distribution, be it normal, ولا be it skewed, ولا be it flat, ولا whatever. If you take the average and you go 2 standard deviation up and 2 standard deviation down, you will capture at least 75. طب ليش قلنا at least? Because once you start working with the normal distribution, يعني the bell-shaped distribution, you can actually say things more specific. You can say if you take the mean and you go down 1 standard deviation and up 1 standard deviation, you will capture 68.2 of the observation. If you go up and down 2 standard deviation, هون نحن كنا عم نقول 2 standard deviation ما هيك؟ Okay. So when you do the same thing in a bell-shaped distribution, يعني in a normal distribution, you will capture exactly 95.4 of the data. نحن هون قلنا at least 75 يعني 75 or more, which is true. But if the distribution is normal, I can be more specific. I can say 95.4. And if I go up and down 3 standard deviation, then I will capture 99.6 of the data. Let me show you the graph. So here's a normal distribution. The mean x bar is 50. The standard deviation is 10. So going up 1 standard deviation, you get to 60, then 70, then 80. And if you go down 1 standard deviation, you go down to 40, 30, and 20. Okay? So this is saying that within 1 standard deviation from the mean, you capture 34.1%. So 34.1% if you go up 1 standard deviation. If you go down 1 standard deviation, you will also capture 34.1. And these two together would be 68.2. Let me go back 1 slide back. Remember, I said 68.2. Okay? So بما أنه the normal distribution is symmetrical, if you start from the mean and you go 1 standard deviation up, the quantity of the observation you will capture is exactly the same to if you take the mean and you go 1 standard deviation down, you will capture exactly the same amount of data. Now notice, when you go another standard deviation, this time you will capture less. So in the first standard deviation, you captured 34.1. Look at this blue area, how big it is. In the next standard deviation, you will only capture 13.6% of the data. Okay? But the same thing if you were going down, come in 13.6. Okay? Now, if you add up the 13.6, the 34.1, the 34.1, the 36, the 13.6, هول مع بعضهم will get you what I said a minute ago, which is 95.4. Okay? And by the time you went 1, 2, 3 standard deviation up and 1, 2, 3 standard deviation down, you've almost captured تقريبا everything or 99.6% of the data. This is true only with normal distribution. يعني the data is symmetrical, bell-shaped. Okay? Whereas if you had a distribution that was skewed, so if we were working in skewed data, okay, and if you were told that in this skewed data, let's say here, this data is skewed to the right, and you were told that the mean, for example, is equal to 100, and you were told that the standard deviation is equal to 10, sorry, 10. Okay, so that means according to the rule of thumb, if you go one standard deviation up and another standard deviation up, so that's 110, this is 120 right here. And if you go one standard deviation down and another standard deviation down, so that's 90 and 80. According to the rule of thumb, between 80 and 120, this area here in between is at least yani greater than or equal to 75%. And this is coming from what I said right here. Okay? All right. Now, this slide, I'm going to skip it here. Maybe we'll talk about it in class. It's not that important, so I'm going to skip it here. Maybe we'll talk about it in class. Let's look at the central tendency. The standard deviation, why do we divide by n minus 1, not n? I already explained that. Another measure of spread. So regarding measure of spread, we talked about the range, we talked about the interquartile range, we talked about the standard deviation. There is something called the coefficient of variation. The coefficient of variation is the standard deviation divided by the average, and you multiply by 100. What that does, when you take the standard deviation, I mentioned that. I did say that the standard deviation has the same unit as the mean because you took the square root. So your standard deviation has the same unit of the mean. If you take the standard deviation and you divide it by the average, you get something that does not have a unit. It loses the unit. It's unitless. يعني مثلا if you were looking at something that was measured in kilogram, the standard deviation unit is kilogram, the unit of the average is kilogram. So when you take the standard deviation and you divide it by the average, kilogram on top, kilogram on bottom, they cancel each other and you have no longer units and you get something that is unitless. The coefficient of variation is unitless. It's also referred to as the relative standard deviation in some of the books. Okay, the coefficient of variation is good when you want to compare apples to oranges in terms of variability. So let's suppose you're looking at cholesterol level and you're looking at fasting blood sugar, and you want to know, do people vary more regarding their cholesterol level, or do they vary more regarding their fasting blood sugar? So I'm talking in terms of variability. Since one is measured using one unit and the other one is measured in another unit, it's not fair to compare them. So what do? Well, what we do is we calculate the coefficient of variation. So I take the standard deviation of cholesterol, 35. I divide it by the mean, which is 160. So that gets me 21.9%. I take the standard deviation of fasting blood sugar, 25. I divide it by the mean, 85. And I turn it into a percentage, so that's 29.4%. And now I can compare the coefficient of variation to one another, and I notice that the coefficient of variation for fasting blood sugar is bigger than cholesterol. So I conclude people vary more in terms of their fasting blood sugar than in cholesterol. Another example that I talk about a lot is, do people vary more in regard to their height ولا to their weight? هل يا ترى في variability أكتر بالheight of people or weight of people? Well, height is measured using centimeters and weight is measured kilograms. So we cannot compare them to one another. Therefore, what you need to do is you need to correct these using the coefficient of variation, and then you can compare them. Last thing about today's lecture, or this lecture, is when we were talking about the central tendency, which one should we use for measure of spread? Well, every time you use the mean, you use the standard deviation. So نحن قلنا we use the mean when the data is symmetrical. So if the data is symmetrical, normal distribution, you're going to use the mean and the standard deviation. What about the interquartile range? Well, every time you're using the median, you're going to use the interquartile range. So if the data is skewed, heavily skewed, you're going to use the median and the interquartile range. The median to tell where is the data, yani central tendency, and the interquartile range to say how much variability there is in the data, yani measure of spread. Okay. Now, percentiles also are used just as an indication of an individual value. So, for example, if you sit for an exam, and for example, the MCAT or the SAT, you're given your percentile so that you know compared to others what have you, how much you fared, and so that's for the interquartile. The coefficient of variation, I said we use it when we want to compare um, measure of spread between two scales that do not have the same unit. That concludes this lecture.